Okay, but yeah, let's go ahead, get started with things on this. So yeah, today for Beyond the Scope, we have Eric from Bruker giving a talk. So he's going to be talking about some of the newer capabilities that Bruker's been working on. I know there's interest from different groups here at CEMAS and OSU on these. So we thought we'd give Bruker a little bit of a time to talk about some of the stuff that they're working on, and we can discuss that. So as anyone has questions, you can pop those in the question and answer or in the chat as well. I'll be monitoring that if you have any issues. And feel free to ask lots of questions. A lot of this is meant to be a discussion. So
Yeah.
I'll pass it on over to Eric.
Yeah, great. Thank you for the nice introduction. As Dan said, I'm Eric. I'm an application scientist working on the nanomechanical testing tools. Thank you very much for the opportunity to come today. I'm happy to answer all your questions when we're over, and I'll also leave my email address up on the closing slide so you can email me afterwards as well. And like you said, today we're mostly going to be talking about new things we've been working on in the in situ mechanical testing landscape. This is just an overview of the talk. I like to have a little bit of an introduction just as a means of orienting people if they're a little less familiar with nano and micromechanics so they can understand what our tools do and how they fit in the broader landscape of mechanical testing. Then I wanted to get into 4 different subject matters. One is looking at dissimilar materials welding. And that's actually kind of a hybrid between platform system and in situ, but there's a reason why I chose to show it. Then we're going to be looking at some advances in automating correlative micromechanics. So doing mechanical testing overlaid with other kinds of analysis techniques. Then I wanted to talk a little bit about some fracture testing and then close by discussing some of our advances in extreme temperature testing, both on the hot and the cold side. This is a really, really basic place to start, but for some people, it's nice to just remember that you could broadly categorize materials deformation into 3 categories. One would be elastic, where the deformation is recoverable, and that's defined by the modulus of elasticity. One is strength, which is related to plastic deformation. That's where you're getting the smooth, continuous deformation as you get past the elastic regime, and you can permanently change the shape of things. And then last, we have cracking, where you grow cracks, usually drastically and suddenly through the material. And this is generally viewed as a very undesirable and unpredictable failure mode. And you'll see these 3 come up all in the talk, where the elastic and plastic characteristics of the material are somewhat easier to look into, but we'll do some cracking and fracture as well by doing some more careful experimental setup. Starting at the bulk scale, there's a lot of really commonly used mechanical tests. I put the tensile test up here because it's really ubiquitous. And this is a good test that gives you a lot of rich, detailed information. And it's good that it deforms the entire sample all at the same time. So you're sampling your entire microstructure and you're going to nucleate failure at the weakest part of your microstructure. And that's important information that nano and micromechanical testing doesn't really replace, but it can supplement it. And you'll see kind of the difference where here we're getting the response of everything, whereas when we do nano and micromechanics, we're building our understanding up from the small scale. But here I wanted to show how, okay, from the stress strain curve of a uniaxial tension test, you get the elastic modulus from the slope in the initial portion of the loading. So there's your elastic property. And we can get plastic properties. Once we start deviating from that linear elastic, we hit the yield strength, and then we can work hard in a lot of cases up to the ultimate strength before it necks down. And so, like I said, a lot of rich information. But when you think about another aspect of this, how long it takes to do this, if you consider the time to machine the samples as well, it's at least tens to hundreds of minutes per data point you're getting out of this. So it comes with a cost in terms of time. Whereas on the nanoindentation side, the tests run pretty quickly. a matter of seconds or even sub-second, in fact. And the fact that we can do thousands to millions of tests on one sample that's been prepared means that it can be pretty high throughput in terms of just getting a lot of tests out on one sample if you're trying to get some statistics out. And, we can still get at the local elastic and plastic properties. That's what's kind of shown in that animation. When you do an indentation test, you're driving a pyramidal probe generally into a surface, and that pyramidal probe has a calibrated contact area as a function of depth. And what we're doing is we've got electrostatic force sensing and or capacitive force sensing and electrostatic actuation on some of our tools. And we have piezo actuation on some of our other designs. But what's common is that we're down in the nanonewtons of force resolution, and we're down sub-nanometer in the displacement resolution. So that's what makes us nanoindentation or nanomechanics. And as we drive this probe into the surface area, we're recording force and displacement. During the initial loading part, we've got a combination of plastic and elastic deformation. But then when we start to unload, it's nearly purely elastic in almost all cases. So we can fit that unloading stiffness to get an elastic modulus measurement. That would be the reduced modulus, which is the stiffness divided by the contact area squared plus some other geometry terms. And we can get the plastic properties through the hardness. That's the peak force divided by the contact area. These are not directly analogous to what you get out of uniaxial tension tests at the bulk scale, but we can convert them pretty easily. Reduced modulus converts to elastic modulus just by considering the fact that the tip deforms a little bit at the same time as the sample. It's actually a pretty small correction. That's what's shown on top. Then in terms of hardness, going back to yield strength, all you have to do is take care of the fact that the stress state is different between an indentation test. It's quite triaxial because as you're pushing into the material's confined in 3 of the directions. Every direction except for straight up, basically. And so it has a hard time deforming uniformly. So you have to use a constraint factor to convert from this to a uniaxial comparative stress state. And this has been done by empirical data correlation. And you can find constraint factors that apply to a class of materials really well. So example, metals usually use 3. So if you divide hardness by 3, you get back to an equivalent yield strength. And then we want to talk about the advantages. Like I was saying before, you're building up your understanding from the small scale upwards. That allows you to do very site-specific tests, indent particular parts of a microstructure or different parts of a damage gradient or a weld zone or things like that. And then it's also great for testing things that are already nano or micro scale, like a thin film or a nanoparticle, things like that. And so there's a practical example of both on the slide. On the right-hand side here, we're indenting different parts of a carbide inclusion on a steel, so we can measure one phase at a time. And on the left-hand side is actually an in situ TEM experiment from my PhD thesis. It's squishing a silicon nanocube inside the TEM. And you can see the dislocations nucleate at the top corner of the particle and traverse down the center. And you can kind of observe how the deformation's happening while you're getting the mechanical data side by side. This is the instrument we're going to be talking about that can do this kind of work. This is the PI-89. And basically the way it works is on the right-hand side is where the tip and the force sensing and all the actuation is happening. And on the left-hand side is where the sample goes. And that sample assembly is on a slider, so you can fit a variety of different options on there. It's a really modular system where you can add on the components, do different kinds of experiments, and you'll see some of those in action as we go on. On the right-hand side, the transducer is quite configurable. We can switch out different load ranges. We have 10, 500, and 3,500 millinewton max force transducers. So you can choose the right force range and get the best sensitivity for the experiment you're doing. And then we can actuate up to 150 microns with our piezo flexure actuator. And that's intrinsically displacement controlled. or we can also actuate our low load transducer electrostatically. So there's a lot of versatility in the testing modes you can do. And how it roughly works is in the image in the bottom right. When you mount this on the SEM stage and tilt the entire SEM stage, you get a field of view that allows you to see your sample and your tip simultaneously. So depending on your test configuration, you might tilt between 5 and 20 degrees on the SEM stage, and then you can see everything that's going on. When I introduced the beginning, I focused on nanoindentation because that's the classic testing mode. But I just want to briefly point out we can do lots of other stress states as well. This does slow down your time to test because now you got to usually make special sample geometries, kind of analogous to the bulk scale. But we can do compression testing on particles and pillars. We can do bend testing on cantilevers. We'll see examples of both cantilevers and pillars later on. I won't get into any tension testing, but you can do that by doing a direct pull with a gripper tip, grabbing a dog bone, or we have a push to pull chip that allows you to do nanowires and lift outs. And then there's also fatigue, which incorporates a dynamic component on top of the quasi-static component, as we call it. And then tribology is where you're doing normal and lateral forces and actuation all at the same time. So you can measure friction coefficients and do wear testing. I'm not going to run through the full list of options, but we've got a lot of different options you can add on to make this system configurable. Just to give you a feel for, all of the different modes we've developed over the years. And then some of these will be shown directly anyway, so I won't dwell on this slide. And so to sort of summarize this, hopefully this has been a good orienteering into how nanomechanics fits into the mechanical testing landscape. In length and force scale, it fits between an AFM and a microindenter. It's very complementary with bulk scale testing because you really cover a very different force and length scale, like I was saying before. It offers a nice set of force and displacement for doing individual phases and a lot of common engineering materials, for example. So with that, I want to start getting into the case studies. And this one, I felt like I should really show because it involves the Ohio State University. This is mostly Daniel Sorensen's work, who did this as part of his master's thesis in the Ohio State University with Antonio Ramirez. When he did this work, he was at Medtronic, and I was heavily involved along with a few other collaborators in industry and academia who are listed on the slide. So this is all about looking at welding zones. So the driving force behind this is medical devices. These are interesting test cases because the medical device industry has some unique demands on its structural materials that can drive them to look at some more exotic material cases. This example is looking at bulk metallic glass. Bulk metallic glass is very biocompatible, and it is very hard and has near net shape castability. And the only real downside, well, there are maybe some other ones too, but the biggest problem with bulk metallic glass is that it's hard to form it into really large pieces. So the idea was to look at whether they could weld bulk metallic glass to titanium to be able to utilize its good properties as maybe an outer layer on one of these medical devices. And that is a significant challenge. When you are welding dissimilar materials together, there's a whole lot of rapid heating and cooling and imperfect material mixing. So you could form a lot of different phases in this weld pool. And so that's kind of what we're seeing here. This is an initial unoptimized welding setup of welding the titanium to the Vitraloy 105 bulk metallic glass. In the center is the weld pool. You can see it's hundreds of microns in size. So there's a pretty small scale. And within, we can see a lot of different little small regions that are, heterogeneous. So to get in here and understand the mechanics that's going on in these different regions of the weld pool, you really need to look towards nano and micromechanics. And so one of the things you see, there's swirls of material, which indicate that there hasn't been perfect mixing in this initial unoptimized laser welding setup. And so when you look at the EDS spectra of the weld, what you basically get the sense of is that some of the regions are very titanium rich and some of the regions are very zirconia rich. So that would be representing the vitroloi because its primary element is zirconia. And then some of the other regions are just better mixed than that. So those are kind of the three dominant regions of the microstructure: the well mixed, the titanium rich, and the zirconia rich. So this was a very comprehensive study where they looked at a lot of different quality metrics of the weld pool to help them do statistical analysis to derive the best welding conditions they could do. I'm just focusing on the nanomechanics part because that was one of the inputs. We went in here and we did hardness mapping across the weld pool. And this was done with the platform system because this was long ago, but you'll see the PicoIndenter side come in after we talk about this map. But nowadays the PicoIndenter has mapping mode as well, so it could do this kind of work in addition. So here you see a hardness map going across the weld pool. On the bottom, we've got really low hardness. That's related to the titanium base material. And in the top part of the graph, we've got more of a intermediate hardness. So that's the vitroloi 105. And the weld pool is in the center. And you can see there's kind of an interesting hardness distribution in there. And this is useful to look at because if you form some brittle, hard intermetallic phases, they would probably be of high hardness. So this can be an input into understanding, what's the distribution of mechanical properties within this weld zone. We can go ahead and zoom in on just the weld pool itself, cut the base materials off, and you can see the hardness distribution in here kind of looks like there's still multiple peaks going on. So there's probably multiple different phases correlated to those different regions of chemistry that we showed before. And to go through and analyze these by hand and assign them would be kind of time consuming. So I wanted to discuss something we've actually done more recently than this weld pool work. This is clustering. This is a technique we've been using to analyze large data sets of indentation really fast. And the way it works is hardness and modulus are the material properties we're measuring with indentation in a high throughput manner. So you could plot the resulting data points in hardness versus modulus space, and then try and group them together into areas that are similar. And clustering lets you do it automatically because it's basically a rudimentary machine learning technique. You can use a few different algorithms, but here we're using k-means. And the way that works is it just randomly puts the cluster centers down, and then it looks at the mean squared distance of all the data to its nearest cluster center and tries to re-optimize that. So it just reiterates until it's found the optimal place to put the cluster center, and then it can split the data into however many groups you ask for. And this is something we've published a couple papers on in recent years. The right-hand example is a dual phase high entropy alloy they were considering for nuclear reactor materials, and we are doing it as a function of temperature, separating out the two phases and looking at the hardness and modulus as a function of temperature. The comparison between the clustering and the manual assignment was really pretty good, but the clustering was instantaneous versus the manual one requiring many, many minutes to go through and sort even these very small maps of 144 indents together. So I wanted to go back and apply that technique to this previous work we did on the weld pool. And when you do that, you can actually cluster this pretty well into 4 groups. One is titanium rich, like we talked about before. One is the zirconia rich intermetallic part. And one is the more well mixed region. So both the well mixed region and the zirconia intermetallic seem to have pretty similar hardness in terms of statistics. Then actually we needed a last cluster because we were growing some titanium dendrites, which are pretty low hardness from the titanium side of the weld pool. And so this is the kind of statistical information you could use to sort of rapidly quality check different kinds of welding conditions. And here's the PicoIndenter side coming in. We also wanted to look at that third property, not just hardness and modulus. We wanted to look at toughness. So we put cantilevers in the weld pool. There's 15 of them in here, and we deformed all of them and looked at basically the amount of mechanical work that went into failing these different cantilevers. And you can see that result over here in looking at the load displacement curves of these 15 cantilevers. There are 3 primary failure modes in here. There's brittle, where you're getting only linear elastic deformation and then they fail suddenly. And that is similar to the brittle parent material, which is the Vitrolloy 105. And then in the ductile response, we're getting a lot of load displacement. We're going well beyond the linear part of the load displacement curve. It's curling over. We're getting well into the plastic regime. And so the amount of mechanical energy these cantilevers can absorb is related to the area under this load displacement curve. And then we had some mixed response as well. There's some limited plasticity, but they still failed catastrophically. And just to visualize that directly, here are the 3 responses in terms of the postmortem SEM images. On the left-hand side is the ductile response. You can see the cantilever didn't actually even fail. It just became a full plastic hinge. In the center is the brittle case. It failed catastrophically and rapidly. And you can see the fracture surface is actually quite smooth as well. And on the right-hand side is the mixed response. So you still see a catastrophic failure of the cantilever, but there's some material pulling out, indicating some ductility. And so it's really, giving a much tougher response if you can get this more well-mixed regions formed in the weld, which is what you would expect. Dan did not stop there. He actually went and lifted out 3 of these cantilevers and did postmortem TEM as well. And you can kind of even solidify the story a little bit further now. The titanium-rich ones, you can see a lot of ductility, twinning, and shear banding happening in those, whereas the zirconia intermetallic doesn't allow a lot of plasticity to happen. Whereas in the well-mixed region, you're getting that additional toughness and a little additional plasticity because you've got this ductile titanium phase that accommodates some of the slip and allows you to get a little more energy absorption before failure, which is nice. And so I wanted to point out too, we didn't calculate K1C fracture toughness for these because you need to know a lot of things about the material, the yield strength, as well as the elastic modulus. So that would require, and the material is really mixed. It's changing location to location. But for the purposes of just understanding the differences in toughness, just looking at the load displacement curves is sufficient. So that's kind of where we stopped on that study. This next case study is something we've been working on with NIMS, which is about automating correlative nanomechanics and micromechanics. And Kevin Schmalbach here at Bruker is kind of leading the effort on our end. So the motivation for this is basically as follows. This is a map of looking at the hardness distribution in an additively manufactured grade 91 alloy. And this is a ferritic martensitic alloy. And you can see in the left-hand side, we've got an EBSD inverse pole figure of the mapped region from the indenter. And on the right-hand side, you get the hardness map overlaid on that image quality data from that map. And there's this dark phase that forms particularly near a lot of grain boundaries, and that's giving a really high hardness response, and that's the martensitic phase. This microstructure is really not very equiaxed because this is the as deposited condition. You'd need to do some additional heat treatments, but this was kind of part of this work. The idea though is like having this data is valuable, being able to correlate the structural to the mechanical properties. And so having a way to do this easier would be nice. For this particular case, this is an SEM image of the maps. We were just indenting blindly. We went out and performed the indents and then went back and measured it, put it into the SEM to do the EBSD. And to do that, we needed to use fiducial marks to find the same area of interest. And so that slows you down a little bit. It would be nice to be able to do this all seamlessly with one instrument. And then there's also the problem of what if you want to search for an interesting region in the SEM and then go over and do the mechanical tests in a targeted way. So how would you do that? So that's the motivation for doing this correlative in situ nano and micromechanics. And to that end, we've basically developed a software package together with hardware with this rotation and tilt stage that allows the user to basically look at 3 different orientations of the sample and move seamlessly between them. And so using the rotation tilt stage, you can align to the indenter and do a mechanical test. And you can align pointing straight up at the electron beam column to do top-down imaging or EDS measurements. And you can also angle the sample then to get an EBSD condition. And the software does all these moves seamlessly for you. So here's an example of it actually running. Here it's in indentation position to start with. And then it tilts straight upwards to look at the electron beam as a top-down. Then it'll tilt over to get to EBSD tilt as well. Okay, so I wanted to show a couple quick examples of what this can do. This first test case is looking at a 410 stainless steel laser cladding. It's a powder that's been melted with a laser and deposited onto a 4140 steel substrate. And the idea behind this is to save some money by putting the stainless steel, just a thin layer, to give corrosion protection to a cheaper steel substrate effectively. And when you go and find this interface in the SEM, in the top-down configuration, you can actually see from the backscatter a pretty strong contrast difference between the heat affected zone in the 4140 and the base steel substrate. And then you'll see from the EDS as well that we can easily draw this boundary between the 4140 and the 410 as well. And from this top-down image, you can just select a few different positions to quickly test and understand what's the property distribution going left to right across this heat affected zone. And so the software can directly go ahead and do those indents. And from the EDS as well, this is where you can see that the chromium is in blue. The chromium concentration is really high on the right-hand side of this boundary, and it's much lower. So that is what we're seeing, 410 on the right, heat affected 4140 in the center, and then the base 4140 on the left. And when you look at the hardness distribution as you go across, you roughly get a nice looking bell curve. So the hardness rises in the center of the heat affected zone of the 4140 substrate and then drops again as you get into the 410 laser cladding layer. Another example with a little bit more indents, this is a niobium and copper accumulative roll bonded nano-laminated material. And so here you can clearly see the niobium and copper layers in the EDS map, and then do mapping over this region and get the difference in the hardness and modulus of the 2 different materials built into this accumulative roll bonding. And so the niobium modulus is much higher than the copper, which is what you'd expect. Interestingly, though, the copper has a higher hardness than the niobium, which is maybe not so intuitive because copper is often thought of as a pretty soft metal. But when you actually look at the EBSD, then you understand that the copper in blue has a much finer grain size than the niobium. And so that's the source of the much higher hardness in the copper layer. So with that, since we're talking about the rotation tilt stage, I also wanted to show you an example of doing fracture toughness directly. This was fracture toughness of pillars, and this uses the rotation tilt stage as well. This is something we did in collaboration with Sandia. And this test geometry is a wedge-loaded double cantilever beam. And you need the rotation tilt stage in order to align this wedge probe with a notch on this pillar. And as you push the pillar in, or the wedge into the notch, you basically split the pillar in half, kind of like a log splitter. And what this gives is multiple crack advances and arrests, which is what you need to do fracture toughness. So here's a video of the experiment running. We're pushing this wedge into the notch, and we'll see linear elastic loading first, and then we'll get up to our first big load drop. And you'll see that this is much higher in force than the subsequent ones that follow. And you can see the crack nucleate out of the notch. And then as we continue loading it, we keep getting load drops one after the other. And in each one of these load drops, you'll see the crack grow by a pretty well-defined increment on the SEM video correlated to it. And so this is kind of a nice experiment because what you need to do fracture toughness is get the mechanical energy going in and relate that to an amount of crack growth that you're getting in the sample. So here we're just testing silicon. This is kind of a base material to benchmark the technique, and then the idea is to move on to some more interesting test cases in the future. What you get out of each load drop is the force before the load drops, and then a compliance fit. So you can see that the force is going down and the compliance is also going down as the crack grows, which makes sense. As the crack grows, the pillar becomes less stiff. And from each of these force and compliance fits, we can put this into a finite element model to get back to the stress intensity that's going into it. And this was what the collaborators at Sandia particularly did. So we can see that the initial load drop in the far bottom right graph is at a much higher apparent toughness, around 1 to 1.05. And then afterwards, the fracture toughness drops down to a much lower value on both of these test pillars. And so the first load drop's a bit higher because we're making the crack appear out of a notch. The notch is not perfectly sharp, and it could be embrittled, or, well, not embrittled, but changed by the gallium fib process that produced it. And then you get a much more consistent response afterwards. And since this is silicon deforming on the 111 plane, you'd expect K1C to be around 0.7 MPa root meters, and we got pretty close to that in this case. So that was kind of nice. So kind of wrapped up some of the things talking about the rotation tilt stage. I wanted to get into the last bit, where we're going to be looking at high temperature and low temperature testing as well. The first test case is a nickel superalloy, and it's got a nickel aluminide diffusion bond coating on top of it. And basically these coatings are here to protect the superalloy from really hot temperatures inside a gas turbine. They need to drop the outer temperature from almost 2000 degrees down to a much more reasonable 500 to 900 degrees C in the superalloy. These are complex multi-layered structures, but you'll see we'll do some mechanical testing in each of these regions. And we want to do this as a function of temperature because we want to look at how the material responds at these operating temperatures. So to do that, we're adding heaters onto both the tip and sample side. This is how the heating system works. These are both independently controlled, so it allows you to get a good temperature match when you're in vacuum. You can't use convection to make sure you reach thermal equilibrium. You have to heat both sides independently and get them matched to each other to get really nice low drift results. And then we've used some thermal breaks and water cooling to make sure the heat doesn't flow out of where we're interested in having it and get into the system where it could cause drift in the stages and things like that. Yeah, we use mechanical sample clamping to hold the samples in place because a lot of adhesives will not work up to high temperature as well. So here's some mapping at 500 C going across this interface. You can see the low hardness region where the superalloy is, then the nickel aluminide, which is much harder. And then even harder between them is this interdiffusion zone, which has a lot of carbide precipitates in it. And we can actually do this as a function of temperature. Here, since they're a little bit smaller maps, you can just draw the manual boundary to do the statistics and look at how the hardness and modulus change in the different regions as a function of temperature. Kind of similar to some of the other work we were looking at before with that dual phase high entropy alloy. And so you can get this kind of data out of how the mechanical properties shift as you heat up. We're seeing that the modulus is dropping slightly, but the hardness is dropping more rapidly, which is what you'd roughly expect out of most metallic materials. So that's how you can get the statistics out and look at them phase by phase. But if you want to visualize the deformation mechanisms and understand what's going on, you can do more controlled geometries. So we're going to do a little bit of pillar compression here. This is looking at square pillars, 8 to 10 microns side length and about 20 to 30 microns tall. And so as a function of temperature in the nickel superalloy, you can see that it's ductile at all temperatures, which is roughly what you'd expect. There is some difference in how the slip steps are arranged on the pillar surface as you go up in temperature. They're becoming more concentrated at higher temperatures, which is interesting. But overall deformation mechanism is not changing, which is not the same when you talk about this bond coating pillar. These are where you've got these precipitates of carbide with our chromium and tungsten rich. And so this is deforming at 800 degrees C. You can see that this material's behaving fairly ductily. The load displacement curve turns over and has a lot of plastic deformation in it, which is to contrast at room temperature, it's a lot more brittle. You'll form a lot of micro cracks in the material, although it's not fully brittle because these cracks actually seem to be deflected by the precipitates. They run into the precipitates and change direction. So you're getting some toughening out of it at the room temperature case. When you go up to high temperature, it looks quite ductile, and it is. But what's kind of interesting was the deformation mode. When you look at the pillar surface, you can see that actually the grain boundaries appear to be sliding, at least 2 of them on the pillar surface. If you look at the red and orange arrow, as we increment the strain, you can see these grain boundaries sliding in the material. So that's a pretty interesting deformation mode. Briefly, I want to talk about a little bit of indentation at 1000 degrees C too. This is something we recently did with the University of Bristol. This material is a TRISO fuel particle. Basically, it's like a futuristic nuclear fuel where the fuel comes pre-encapsulated with these outer layers to protect it. And also in theory, that allows it to run up to higher temperatures and be more efficient as well. We're testing surrogate fuel particles, obviously, but what we're looking at is the outer protective layers up at high temperatures to see how well they provide mechanical protection up to 1000 degrees C. And so the intent was to actually test the graphite phase as well, but what you can see in the image on the bottom left actually is that there's a big step height that's grown between the silicon carbide phase and the graphite phase next to it. And that's because at 1000 C, the graphite actually started oxidizing even in the SEM with a really good protective environment going on. So we ended up just indenting in the silicon carbide phase. And we're doing continuous stiffness by doing our CMX technique. So we can track the hardness and modulus as a function of depth, even up at 1000 C. So that's the video you're seeing on the left-hand upper side is the indent occurring up at 1000 degrees. And we can get pretty nice looking videos as well, even though we're running pretty hot. When you look at how the depth profile comes out, there's a slight drop in modulus with depth and a more extreme drop in hardness with depth. I think some of that is just the fact that as you're driving in deeper, you're feeling this open space to the sides where the graphite's oxidized away. But you can't necessarily neglect also that there can be some tip blunting when you test at high temperature. And maybe there's actually some chemistry difference as well. Maybe there's some oxidation happening in the silicon carbide. But if you take the data anyways and plot it against literature trends, we can see that we fall on a pretty similar line to some previous work that went up to 500. And so overall, what you're seeing is a huge drop in hardness going from 40 GPa down to 10 at 1000 degrees. And that's accompanied by a pretty big change in the deformation mechanism. On the left-hand side is a room temperature indent. There are radial cracks coming out the corners of those indents, indicating it's very brittle. And at high temperature, we don't see any cracks. We in fact see some slight signs of pileup around the indent, indicating plastic deformation. But yeah, this is a nice example of taking the literature data and pushing it out to a little bit higher temperature range. Getting up to 1,000 degrees C and doing clean mechanical tests is it's a new frontier in mechanical testing. It's only a recent thing, relatively speaking. The last temperature direction to go is cryogenic, and I'll do this a little bit quicker. The way this system works is just that we're running a setup that's pretty similar to the high temperature setup because we've got those heaters there, and that's how we're doing all of the temperatures from our base temperature up to room temp. We can heat up and control all the intermediate set points. So what we need to do is bring in that cooling power to bring the temperature down. And the way we do that is we have a liquid nitrogen dewar that flows liquid nitrogen up through a transfer line, and it comes inside the SEM, comes to the feed through and splashes against this copper plate that's inside the SEM, but the liquid actually doesn't flow inside the vacuum at all. That's a pressure difference there. And so from there, we've got that liquid nitrogen temperature where it's splashing against that copper plate on the feed through, and then we just conduct it down to the PicoIndenter using a large copper braid. And then we split it off to go to both the tip and the sample side. And that gets you down to at least minus 130 C, but we can go a little bit colder. Since every chamber is a little different, we need different lengths of the big copper braid. So the temperature spec is a little bit more conservative than our optimum. So this is minus 140 C, deforming a nitronic 50 stainless steel pillar. And this material is actually pretty ductile, even down at cryogenic temperatures. This is an example of a material that's designed for use at cryogenic temperatures. So it's maybe not so surprising that it still retained really good ductility. And so what you'll see during this video is we're in the linear elastic portion now, and then it'll turn over, get into the plastic region, and we'll see a lot of nice ductile flow happening on these slip steps that are parallel oriented across the center of the pillar. I did note that, you do see some slip steps already because this is the second test cycle. The first one is just not as exciting. So in the interest of time, I just wanted to show the second test cycle where we get a lot of plasticity out of this pillar. And actually we compared this against our platform system, which does cryo as well, doing nano indentation. I'm converting from hardness divided by 3, which we talked about at the beginning, against the yield strength of these pillars, and they fall on a pretty similar line. What we're seeing is though roughly a doubling in the yield strength when we go from room temp down to minus 140 C. I also did a little bit of tungsten pillars as well. This is also pretty ductile, even down to minus 160. These are all roughly singular grained, but you'll see that the yield strength goes up quite a bit as a function of decreasing temperature. Here are the true stress, true strain curves you can calculate out, and you can see that, there are some apparent differences in what slip systems are active in these different pillars. At minus 160 C, you've got one gigantic slip step that keeps deforming, whereas you're kind of more in multi-slip at the minus 80 temperature, but still yield strength, again, roughly doubling from room temp down to minus 160 degrees in this case. So with that, I kind of wanted to wrap up and just recap some of the things we talked about today. Nanomechanics and nano indentation really offer a unique testing length scale and force scale that is complementary with bulk scale techniques, and it's really good for looking at heat affected zones from laser processing, which is really popular these days, but also things like nano and microparticles and microelectronics. We can do a lot of different loading modes to explore different kinds of deformation behavior in materials. And you see in a few of the case studies I showed that we're blending high throughput testing to get statistics and more targeting experiments to visualize the deformation mechanisms through things like the pillars and the cantilevers, which is a good approach. And I showed some of this happening at extreme high and low temperatures, like we talked about. And I think we're always looking for ways for the future to further automate the analysis and automate correlating the mechanical testing with other techniques to help you do structure property processing relationships fast. And I really believe that's where the future of our field is going to. So with that, I'd like to just take some questions. You can also email me later at my email address at the bottom of the slide. So thank you very much for your attention, and it was a pleasure.
Thanks a lot, Eric, for giving the talk. I enjoy always hearing more about in situ, and I really enjoy